The intelligent headlamp system automatically activate the low and high beam and adapt the light distribution according to the traffic situation. This electronically controlled system is challenging to design and test because of the complexity and number of interconnected system components, such as cameras, software, and electronic hardware. Other challenges include testing drive scenarios at night conditions and the collaboration between different engineering disciplines to design systems that meet the required safety, performance, and comfort. The rising complexity of today's electronic systems and software demand a robust development methodology. We are going to show in this video how an interoperable Ansys digital toolchain allows to design and simulate safe electronic control system for automotive. The solution is fully integrated and compliant with safety standard ISO 26262 and design standard AUTOSAR. We start from the system requirements, which are the description of what the system should do and the constraints on its operation. The system requirements are captured by systems engineers in a connected requirement management tool such as Polarian and then automatically imported into the Ansys system architecture modeler. Here is an example of system requirement. The intelligent headlamp system shall communicate with other systems over a CAN bus. The system architecture is developed following the MBSE model-based system engineering methodology to support the design, analysis, and verification of the complex headlamp system. In contrast to document-centric engineering, MBSE puts models at the center of system design, with multiple abstraction levels of modeling from operations and use cases, functional decomposition, and physical architecture. The architecture model is traced to system requirements that are synchronized with the requirement management tool. In this internal block diagram of the system, we can see the different system components and their connections, such as the headlamp cockpit controls, the different control units, the CAN bus, and the right and left headlights. Ansys Matheny is used for safety and cybersecurity analysis. Both safety and cybersecurity analysis are integrated and connected to a model-based system architecture model that is considered as the source of truth. In the headlamp demo, the architecture is imported from SCADE Architect. Any update in the system model updates automatically all the impacted analysis. Matheny complies with both ISO 26262 for safety and ISO 21434 for cybersecurity. Matheny for cybersecurity allow to assess the security risks inherent in the system design. Key methods are supported, such as attack trees, threat scenarios identification and vulnerability analysis, and promote a security by design approach with well-defined risk assessment and mitigation methods. Looking now at the fault tree diagram and the safety analysis, we see that a major failure event on the left headlamp can originate from either a physical light failure or from the failure of the control unit. To meet the safety goals, a safety monitor subsystem is required to detect a failure in the control unit and activate a backup mode with a standard lighting system. This is formalized in a derived safety requirement that is pushed into Polarian and then pulled in SCADE Architect for the system design team. As we can see in the block diagram, the system architecture is updated in SCADE Architect to add the safety monitor and the backup system. The software architecture of the headlamp control unit is fully compliant with the AUTOSAR standard. It's broken down into application software components, runnable entity, and timing events. The software architecture block diagram is automatically synchronized with the code generation model, designed in SCADE Suite. All the software blocks, interfaces, and data types are automatically imported, easing the transitions between architecture and coding activities. The software components are managed as library items, which are small independent units that can be composed and reused. SCADE code generator is qualified to the highest safety level and the generated code compliant with ISO 26262. A simulation panel can be quickly created to drive rapid prototyping and functional debugging. The solution allows achieving full requirement-based testing, including model and code coverage. The application software is then automatically generated and deployed on the electronic control unit. Ansys AV Accelerate allows modeling physics-based visual cameras and LiDAR sensors and simulate driving scenarios with high fidelity. The skate control software model is co-simulated with the camera model to analyze and validate the headlamp design for multiple scenarios involving surrounding vehicles, pedestrians, curved roads, and night conditions. There are several benefits for this solution. First, it allows designing safe system architecture fully compliant with safety standards, and validate early the control software before building costly physical prototypes. The interoperable Ansys tools jointly allow better collaboration between engineering disciplines, easy transitions between design phases, and building better and safer products.